everyone. Thanks a lot for being there again for the afternoon of the PixFoundation workshop. This afternoon, we have a series of talks, exciting talks. We have also spotlights and then a panel and awards. And it's my pleasure to introduce Xueyan Zou. She's currently a postdoc at UC San Diego, but she worked in different universities in US. She has a series of influential work on foundation model, and in particular on semantic interfacing language and vision. Her work is at the crossroad of computer vision and robotics, and it's actually echoing with the topic of today's talk, right? So let's give a hand to our next speaker, please, and let's start. Thank you for being there.
Thank you for the nice introduction, and let's start today's talk. So, in line with this workshop, my topic is on pixel foundation model and intelligence embodiment. During my PhD research, I spent most of the time actually on understanding pixels. And after my PhD, or at the end of my PhD, I started to work along multimodal understanding or large multimodal, something like that. And after my PhD, I go into the direction of scene representation learning and intelligence embodiment and try my best to leverage the information I have learned during my PhD. And yeah, today's talk starts. So visual perception starts with the pixel. When structured pixels come together, they form parts. As parts combine, they give rise to objects, such as an apple. When multiple objects are arranged meaningfully, we create a structured image like an apple tree. Images can be viewed from various perspectives. If we animate the view, we move beyond the static image to a scene. When we introduce the dimension of time, a static scene gains motion, evolving into a video. This is how we experience the visual world in our daily life. As a continuous flow of dynamic scenes, videos taken by camera mimic the way humans perceive the world every day. In high level, the visual perception range from pixel to video quantifies human perception, breaking it down into a structured format that machines can understand. This framework allows us to describe the entire human perception space in a way that is interpretable by machines. To describe the visual world, language are invented by humans. It is the implicit manifold that describes humans' imagination, world with a basis on physical reality. Thus, vision and language are naturally aligned. This alignment is actually the key component in foundation model that build towards general simulation of human intellectual world. With aligned vision language representation, further capabilities are evolved, such as reasoning. And that is in the past 2 years, how large language models and the recent large multimodals or multimodal in, multimodal out, those kind of structure are coming out. And in a line the topic of vision language modeling and large language modeling, we have a serious work. For example, in the multimodal language, multimodal image understanding, we have OpenSeed that is in ECCV 2002-3, and we have and we have DynoV that is in last year's CVPR. That's how that understand parts in a better way. And apart from multimodal image understanding, we have generalist model. What is generalist model? For pixel level understand, we have instant segmentation, part level segmentation, but those are individual tasks. We can combine multiple tasks together. We can add for example, image classification, image captioning in together with those pixel level understanding tasks. So that is the generalist model part. We combine different tasks together using one model to understand them all. And in along that, we have two works in the previous time. One is Axicoder, that is the first work in the series, and that is the theme. I think some of the people here know that, the segment everything everywhere all in one paper. And after that, we have another work called Fine Interfacing Foundation Model Embeddings. I didn't write it here. And after that, after the generalist model, because generalist model is talking about alignment. people are thinking about how are we able to reasoning in the image. Then that is the large multimodal perspective, the third column here. And on that perspective, we have some work called, like, for example, Lava Plus. That is how are we able to understand the image to using tools. And also we have lava grounding. Instead of directly doing Q&A, like with visual input, how are we make the output in align with the spatial location? That is lava grounding. I will not dive into this research today. I will just give a brief introduce, but I will dive into like what I'm currently working on, that is intelligence embodiment. For intelligence embodiment, we can think it has three parts, like to achieve that. For example, as a human, I'm currently talking here and I can walk around. And to achieve that, I first need to have scene understanding. I need to understand like what is inside the room and what does the room look like. That is first column. And second, if I interact with an object, for example, I interact with a microphone, I also need to understand the object. I know that that is a real object. Or if I interact with some like soft objects, I need to have a very good understanding how the object works. That is the object modeling. And the third part, in order to have like workable policies for robots, it cannot like directly train in real environment because that is so expensive and time consuming. For a robot to do one task, maybe it takes like 1 minute, but like it's very expensive if we have like 1,000 robots at one time. So we need to have simulation environments to do robot modeling. That is the third column. And today I will give three works along each of the column and to introduce how we are evolving from pixel understanding to intelligence embodiment. And let's begin with the scene modeling. And the first work I will introduce is the M3, 3D spatial multimodal memory. And that was in this year's at Clear. The motivation for me to do this work is, first, I have really good understanding on foundation models. How to apply that into scene understanding, because definitely foundation model understand the image, it can also understand scene, or it can represent the scene in a better way. And that's the motivation. I start with the 3D spatial multimodal memory. And for example, here's a video, and it has lots of images. And we can extract some raw features from each image. And the image we extract, the feature we extract here can be a clip we have tried in our paper, and can be a C clip, and also can be scene. And we try actually 6 different foundation model as feature extractor. And this is a raw feature. And each raw feature, as we see in the previous slides, like that is a patch in a frame. And for that, each single feature we can project in 3D. And that is the image we show here. And that is the manifold of one video on the left. Video data have lots of redundancies. For example, like if we represent like this table and the adjacent pixel may be very similar to each other, we don't need so many information. And if it is a video, that object have already appeared in the video in multiple frames, so that we also don't need so many informations. Then we do an information reduction, that is project all the raw feature to the memory field. And those red dot here, each dot is like a reduced memory. How we reduce memory? If 2 features are close with each other in cosine similarity by 90%, we'll just remove one. It's quite simple. And that is a result of our memory reduction. And we could see that, yes, the reduction is good. Like the red dot spread on the like feature manifold like of spread out the feature manifold of all the features, so that we have a like effective memory. Yeah, this is raw manifold and raw memory. And scene representation. Previously, people like using NERF for scene representation, but the problem of NERF is that it's so implicit. And recently, people are working on Gaussian representation. And Gaussian representation, we can think about like each Gaussian is a ball, and we represent the scene use lots of those kinds of balls. And and in each Gaussian primitive ball, it has some like features. It has spatial features that represent the XYZ location of the Gaussian ball. And also we have RGB information, like what is the color of this specific Gaussian primitive. And also we will have affine like information, like is the Gaussian primitive at this location in like what its shape is and what its direction is. And also finally, the feature, like in each Gaussian primitive, like it has a feature, sorry, like to represent what like the foundation model feature. Yeah, this is like a Gaussian primitive, and lots of Gaussian primitives formulate the scene representation. And how are we translating scene representation in relation with foundation model? Like those Gaussian primitive features are initialized random, and we use the video to constrain those random features so that we can learn like in each spatial location what is a Gaussian primitive feature is. And for previous models that is shown on the right-hand side, like others, each Gaussian feature will use for the 64 dimensions, like 1 by 64. That is quite a lot of dimensions, like to store like in a Gaussian representation because there are so many Gaussian primitives. And in our model, we propose to reduce the dimension of storage that is 60 dimension. And in the meantime, we are able to reduce the dimension. We use a Gaussian memory attention so that the principal scene component directly attend with the row memory, so that the row memory are able to directly compute the output. And we can see on the left and right, on the left is a previous distillation method. The feature is much less continuous and representative than our Gaussian memory attention because distillation always lost information. And so because we are using this Gaussian memory attention, it uses original row memory features so that the build scene representation is directly in line with the foundation model representation. And here is the visualization result. Above is ours, and down distillation method is like others. It clearly shows that like our method has better, like it's more crisp. The feature is more like aligned with those like the objects, and also it's more continuous. And we have tried like 5 features here. Clip, C-clip, llama V, llama 3, as well as scene. It's quite robust method. And compare M3 with distillation-based method. The first good thing is fewer parameters. For fewer parameters, we see that if we want to scale one scene to a building, like for previous distillation-based method, it needs to run like 67 billion parameters. How about M3? It will only need 8 billion parameters because we store a low-dimensional principal scene component in attention with a row memory feature so that, yeah, it's efficient. The second benefit is better alignment. Instead of distill the original feature, like from foundation model, we use Gaussian memory retention. The weighted sum of the original like row memory formulates like the final output feature. So that it's just directly in line with like the foundation model. We don't need to do anything, so that we have shown like much better performance on grounding performance and much better performance on image text retrieval in the paper. And here is the clear pipeline. I will not dive so deep, but I will give a brief introduction. So we have like multimodal input image. This is a video, and we will make that into the foundation model. We extract row features, and we do feature reduction that formulates the memory bank. If you remember the red dot in the previous images, that is the previous slice. That is memory bank. And then the memory bank feature will do the Gaussian memory retention with the render rate features to formulate the final, Gaussian memory retentions with the Gaussian primitives to get the render features. And the Gaussian primitives, is getting from we have those 3D Gaussian balls, and each one have principal query. And then we project using a linear layer to a higher dimension and do the Gaussian memory retention. That is the first row. And the second row shows that how exactly the Gaussian memory retention is. We have memory bank that is called principal scene components. You can think about PCA is actually very similar, like concept-wise. And we have principal queries that is 16 dimension, and we do a linear projection to a higher dimensionality. And we have this cosine similarity computed between principal scene components and the linear projection. And finally, we do a softmax to do a weighted sum of the principal scene components for the render feature, so that the render feature is directly linked back to the memory bank. That is a frozen feature from the foundation model. That's why our model are able to generate much aligned features than distillation-based method. They are directly predicts the feature in high dimension analysis. And to prove the memory works, that on the left-hand side, that is a principal query. And on the second column, the right dot here, those are not drawn by me, those are drawn by algorithm. I draw thousands of images, and it shows that if traced back to the original row feature, the red dot here in principal query will trace back to this feature, and the blue dot here will trace back to the sky, so that our feature reduction makes sense, that we don't need so many features for a sky, we just need one feature, that's sky. And for the train, this green feature trace back to here, and the yellow dot here trace back to here, and this is the final render feature. And this visualization shows the effectiveness of the Gaussian memory retention. And here are some applications. So basically, we have some we have a view, and we can build a scene representation. And given a click query, for example, a yellow duck, we are able to locate the pixel here, and we can ask the robot to grasp the objects. And here are more applications. This is pick up the screwdriver by its handle and place it on table. And M3 is used for locate the object in the scene. And pick up the sponge and place it into the sink. Yeah, so those are some real robot deployments of our M3. This is the end of introduction of the scene modeling. And we come to the object modeling. How are we able to model an object? Modeling a rigid object is easier, because for example, the phone is a rigid object. No matter how we interact with that, its shape doesn't change. But interact with those soft objects or deformable objects is much harder than rigid objects. And I will introducing a recent work that is in submission to Coral called Graph Language Action Model for Soft Object Manipulation. In this work, we propose using object-centric graph representation as input to large language models for manipulating and controlling deformable objects as shown here. And we have three different kinds of deformable objects we care about in this work. One is a granular that is on the left-hand side. Those are small blocks are able to interact with each other. And also we are working with the clothes that is able to fold. And also we have interaction with a rope that is able to push forward and push back. And graph structures are often used in robotics to represent information related to the environment and tasks that may be performed. A very popular usage of graphs is in, for example, scene graphs for mapping and navigation. For example, here nodes are at some granularity key points within a map, and edges represent their relationship with each other. A different kind of graph representation is also an object-centric one. On the right-hand side, particle-based graphs can be used to represent objects. The nodes are the particles of the objects, and edges can represent some material property. For instance, this rope has a stiffness property. This line of work is by Professor Xueyan Zou's group, as looked into its form of representation for deformable objects as a way to not only control them, but accurately encode the deformation properties of soft body objects. But back to our main point, how are we able to, so back to our main point, how are we able to utilize graph representation in LLMs? And there are some related works. Like for example, existing works are using graphs as a tool for an LLM to query. Is it possible to use the latent embedding as inputs to LLM instead of textual representation of a graph? And here we introduce graph language action model. So for graph language action model, instead of have natural language for the input to the LLM, we have graph embedding input to the graph LLM. And in our work, we have the initial graph state and also the final graph state. That is our goal. And then we go into a TAG conv encoder, that is a graph encoder. And after that, we go into MLP projection layer. And we also encode other state information as well as a sequence encoder that is only used in training. And after that, we predict the actions. Like we have we have some random noise in a tent with graph representation as well as the state information. And we predict the robot action, like how are we able to move the robot arm in interacting with those soft objects. And we collect data to train a model from a series of simulation environments. For example, this is a rope interaction, and the second one is a granular interaction, and the third one is the close interaction. Because we use graph to represent the object, the simulation to real gap is easier to be solved because we are using SAM as a pixel level understanding task, to trace those small objects as well as the rope and close. And we translate that into graphs so that the seam to real gap is not that high. And here is the seam to real graph representation. The first one is a granular, and this is a real graph. We run SAM on that, and we find each chocolate here, and we build a graph. And second, we also run SAM here for each granular that is a node point in the graph, and they have edge connected with each other. And those are some simulation graph. And this is close, how we represent a close as graph, and how are we able to represent row as graph. And because we just simply use graph as representation, simulation real gap is small, and we are able to apply that into real. And I will first introduce our training results. We compare with some adaptive graph, that is some control-based method, and also we compare with large multimodal based method, that is pivots. And the metric we evaluate is after we achieve those actions predicted by the model, the output in comparison with the ground truth output with the transfer distance. How distance between the predicted outputs in relation with the ground truth output. And we can see that in most of the time, graph representation have the best result. And for language, it just translate the graph in language. For example, node 1 location XYZ, node 2 location XYZ, something like that, and edge 1 blah blah blah. So that is the language input, and we show effectiveness of our graph representation. And here are some real demonstration. With the predicted so you can see some those things here is a ground truth, and the predicted action that is input for the robot and to do the action, and the output and input is actually very close. And here is the input, and here's the target output. And we can see that it's quite reasonable for the output in relation with the input. So for future work, like we can improve in simulation for deformable objects manipulation that will help in the quantity and diversity of data collected. And current benchmark for deformable objects manipulation are either closed source, such as the example shown below, or deprecated or like very ancient, like developed 5 years ago or 10 years before. Also, like wish to incorporate more language instruction in the future. That is end of the like introduction, like one of the work on how to interact with the object, how we are modeling the objects. And next work is how are we like do the robot modeling? Like how are we train like policy with simulated robots? And this is a recent work in RSS, like for DEX 1B, learning with 1 billion demonstration for deleterious manipulation. And for deleterious manipulation, like I would say that it's by hand. Instead of using gripper to interact with the object, it use like robot hand. And previous work, like we generate 1 billion, like billion scale data, and previous work only generate million scale demonstration data sets. And as we know nowadays, like data is essential for training models. And so how are we able to scale up? Like to billion scale, like in an economic way, like from million to billion, with lots of computation resources. And like, yeah, how are we able to do that? And is it necessary to scaling the manipulation like data, like from million scale to billion scale? We will answer those questions here. And here's the current techniques. Like there are some optimization-based methods. For example, the DescriptNet, grasp D3 and FastGrasp D3, something like that. Those are like efficient, like the accuracy is good, but it is like they have the those are not efficient. Like generate one control base or optimization base like trajectory is very, very, very slow, like maybe 20 minutes for one trajectory. And not other methods, for example, reinforcement learning to generate a grasping trajectory, it has the problem of limited trajectory. It will just always generate like those kind of like grasping pose and that, like even not generate diverse grasping pose. And that is why like we need our method, like we need generative models like to generate billions like of like data in a scalable and efficient way. Challenge of generative models. The first one is the feasibility. Like it is lower success rate than like the discriminative model or like as I introduced before for the control-based, optimization-based method. Those kind of methods are usually very like the successful rate is high and generative model successful rate is low. How are we able to solve that problems? Like, how are we able to have a generative model that is able to have high success rate? The first solution is we add geometry constraints during training. For geometry constraint, first we add the like approximate SDF loss. For SDF loss, you can think about we penalize if the finger touch into the object. That is penetration. And the second is that we penalize like if the like hand is not interacting with objects. So that is like encourage contact. With those like with the approximate SDF loss, it shows in the table that we increase the like quality, the success rate, the SR, like by a large margin than the previous method that around like 20 points. So like the loss is effective. And also the second question we want to answer is it necessary to generate from 1 million data to billion scale? And our answer is yes. As we show here, as we increase the data scale, the accuracy the accuracy increases by even linearly. Like lifting is like we lifting up an object. Articulation is interacting with object. Both those kind of interactions like are improved with more data. And then yeah, the second problem we want to solve is the diversity. Like the model tends to interpolate when sampling new actions. Like it means that if we don't do something action, the generated data will just lie in the range of the training data. That makes sense. And we actually try to solve that in a better way. How do we solve that? Like we condition on the contact point. For example, if I contact with the microphone at this point, we use this feature as an condition. And if I contact with that point, we use that point, the feature as a condition. In that way, we condition on the contact point to generate a pose so that it comes from like interpolation to extrapolation. And we can see that they are like the pose is very diverse, like when we contact with the WAS. And here's the overall pipeline. And like first we use optimization method to generate some seed data sets. And after that, we use the seed data set to train our like generative model. And after that, like we condition on the contact point. We synthesize many like proposed like trajectories. And then like we use simulation as a critique to evaluate whether the data trajectory is correct or not. If correct, we preserve them. If not, we just remove that. Yeah, and we finally have the debiased data sets, and we can iterative to the procedure to generate more data. And here are some simulation results for grasping. Those are all like real, like real simulation, like lifting like the objects. And also we have articulation of objects, which demonstrate the effectiveness of this pipeline. And okay, those are simulation results. Is that generalized good to real? Like, yes. And the answer is yes. Those are seem to real transfer. It is not replay. It is like we just use the policy. And it shows that like the grasping pose as well as like the firmness is all very good. Yeah, just continue scrapping these different kind of objects. And if you're familiar with like robots, you will feel that the grasping is more elegant. Like, yeah. And also, yeah, I will just conclude the talk. And so maybe I will just go back to this page for conclusion. Like, during my PhD, I started with pixel understanding. And now like I'm much like, yeah, it's a road towards the intelligence embodiment. And I actually believe that in the next 2 to 5 years, the intelligence embodiment is very important. And pixel level understanding, scene understanding, and large language model, large model will help a lot on the intelligence embodiment. And yeah, that's all for today's talk. And thanks everyone for coming and listening. Thank you. The interaction logic. And I didn't have experiment to prove that, but personally, I believe that those kind of interaction objects, like not the philosophy, but the rules are actually stored in a transformer, like we have like learned. And there's a problem actually, because that is like the cross embodiment problem. We use the robot arm framework to do the interaction. And actually, I believe the robot information is also stored kinds of in the like. What do you mean in the model? Yeah, in the model, because like that is the general problems on robotics domain, like the cross embodiment. How are we able to like now we use framework and we change to another X arm? Are we able to generalize the policy? The answer is actually like not very good. People are exploring that. And I believe the specific robot information also stores like in the. So you're saying like the robot actions are entangled with the object present. Yes. You don't have way to disentangle it. Yes. I see. Thank you. Very cool observation. Thank you. Any other questions? Okay. If not, I will pass to the host.
Thanks a lot again.